Yes.
Bueno, primero en español. Bienvenidos a todos los participantes de este ciclo de seminarios propiciados por la Sociedad Colombiana de Catálisis en compañía con el laboratorio CICAT y SurfLab en modalidad virtual. El día de hoy contamos con la participación del doctor Julián Sánchez acerca de valorización de biomasa a partir de la transformación de epóxidos de monoterpenos, quien va a participar con un mini seminario. Y a continuación seguimos con la plática del profesor invitado, el profesor Paul Dauenhauer, quien va a hablar acerca de the catalytic mechanics of dynamic surfaces. Well, thank you very much, Mr. Dauenhauer, for attending our invitation. And well, Professor Dauenhauer is a chemical engineer, from the University of Minnesota, and he is recognized for his work in science and engineering in catalysis. So we are going to start with our partner in the lab, Julián Sánchez, who is already connected.
Hola, entonces voy a compartir la presentación.
Thank you.
Con nosotros el compañero.
Julián.
Sí, acá estoy, ya voy a compartir la pantalla.
Ya estaba compartida.
Sí. Listo, ya ven la pantalla, ¿cierto?
Sí.
Bueno, listo. Entonces, el tema que voy a presentar hoy es algo relacionado con lo que hice en mi tesis doctoral y algún trabajo que se está llevando a cabo acá en el CICAT en conjunto con el profesor Fernando Martínez. Entonces, el título de la presentación es Valorización de biomasa a partir de la transformación de epóxidos de monoterpenos. Mi nombre es Julián Eduardo Sánchez Velandia y esto hace parte del trabajo de investigación que se lleva acá en el Centro de Investigaciones en Catálisis. Bien, entonces, ¿de qué se trata este mini seminario? Primero, una breve introducción acerca de lo que es la biomasa y su importancia, por ejemplo, acá en Colombia. También la aplicación de algunos materiales mesoestructurados y zeolitas naturales en esta reacción de epóxidos. Algo explicativo acerca de cómo se combina el laboratorio con cálculos de FT y finalmente qué estamos haciendo en el CICAT con respecto a este tema. Entonces, como introducción general, la biomasa está compuesta principalmente de celulosa, hemicelulosa, lignina y otros compuestos orgánicos que son de gran interés en química orgánica y principalmente también en química fina. Entonces, ¿esto es por qué? Porque tiene una gran versatilidad, un alto impacto económico, es abundante, se encuentran muchos recursos naturales y además de esto se puede generar valor para los residuos. Entonces, ¿qué pasa en Colombia? En Colombia, en este campo hay muchas oportunidades y retos. ¿Por qué? Porque Colombia es un país tropical, esto lo hace bastante biodiverso y principalmente hago referencia a los aceites esenciales. A los aceites esenciales también hace parte de la biomasa y esta mezcla de compuestos orgánicos están principalmente determinados por una cantidad de sustancias orgánicas que se llaman monoterpenos. Entonces estos monoterpenos se pueden transformar y se pueden extraer de recursos naturales. Además que en este campo, por ejemplo en Colombia, hay muchas empresas que arrojan residuos y que no son aprovechados correctamente. Entonces, valorizar todos estos residuos o valorizar esta biomasa es un tema que es pues, de bastante interés en investigación. Entonces, acá entro a hablar un poquito más de lo que es los aceites esenciales, principalmente de estos que se pueden extraer de fuentes naturales, y me llama bastante acá la atención estos monoterpenos que se llaman el alfa y el betapineno. ¿Por qué? Estos compuestos son compuestos bicíclicos que contienen un gran estrés dentro de su estructura, pero esos dobles enlaces que están acá hacen que puedan ser fácilmente epoxidados o puedan sufrir transformaciones orgánicas. Entonces, en ese sentido, hablo de los epóxidos de alfa y el epóxido de betapineno, cuya diferencia estructural se encuentra principalmente en la ubicación del epóxido. Entonces, ¿por qué son de gran interés? Porque estos compuestos se pueden abrir, es decir, se pueden generar compuestos termodinámicamente más estables, cuya aplicación es bastante extendible en química fina. Entonces, ¿qué compuestos se obtienen de la isomerización de estos epóxidos? Entonces, desde el alfa-pineno se puede obtener aldehído canfolénico, carbeol, pinocarbeol, mientras que desde el epóxido betapineno, mitanal, mitenol y alcohol perílico. Entonces, estos compuestos, todos estos que se obtienen de la isomerización de estos epóxidos, tienen una gran aplicación en química farmacéutica y química médica, por lo cual estudiar los factores que afectan esta reacción es de gran interés. Entonces, ¿qué se ha hecho en catálisis homogénea y heterogénea? Se han evaluado una serie de sistemas catalíticos, principalmente modificaciones con centros metálicos, con el objetivo de controlar la selectividad de estos compuestos. Entonces, ¿qué se ha permitido elucidar o qué es lo que afecta a la selectividad de estos compuestos? Principalmente el carácter Lewis y Browning de los materiales que se estén utilizando, el tipo de solvente y en menor caso las propiedades texturales. Y esto hace que se plantee siempre un nuevo catalizador para controlar la selectividad con el uso de este tipo de sistemas. Entonces se han aprobado diferentes sistemas catalíticos que se encuentran en mesoporosos, microporosos o sistemas que son amorfos. Sin embargo, la selectividad de esta reacción suele ser poco controlada. Entonces, dentro de esta rama y pensando en encontrar un catalizador que sea bastante selectivo a este tipo de reacciones, se puede pensar en sistemas soportados. Entonces, si observamos la figura o sistemas metálicos soportados, vemos que hay diferentes metales que pueden ser promisorios para estas reacciones. Estos principalmente podrían ser los metales de transición, dado que estos metales pueden inducir ácidos tipo Lewis que son favorables para este tipo de reacción. Entonces tenemos tanto el hierro como el cobre, que son bastante abundantes y con aplicaciones industriales. Si bien estos centros metálicos podrían ser bastante interesantes para su uso en esta isomerización, se deben depositar en soportes que puedan tener una alta área superficial y una amplia distribución de tamaño de poro, ya que estas moléculas y sus isómeros son moléculas pues relativamente grandes. Unos soportes que son promisorios para estas reacciones podrían ser la CBA15, la MSM41, aunque son silicios y no tienen acidez, tienen una alta área superficial o cumplen los requerimientos que previamente se había comentado. Entonces la introducción tanto de hierro y cobre a este tipo de sistemas incrementa la acidez y por lo tanto la probabilidad de abrir estos anillos epoxídicos. Sin embargo, muchos de estos sistemas catalíticos que son sintéticos requieren numerosas etapas de preparación o días de preparación, lo cual puede ser que no sea tan viable. Entonces, y con el objetivo de valorizar siempre desde la parte catalítica o desde el catalizador hasta la transformación de monoterpeno, se puede pensar en fuentes naturales y la extracción de estos materiales del magma de, por ejemplo, de las cordilleras colombianas. En este caso, unos materiales bastante promisorios son las zeolitas, específicamente las zeolitas naturales. Entonces, ¿por qué? Las zeolitas son sistemas que son ácidos, pueden abrir los epóxidos y presentan excelentes propiedades texturales. Una limitación de las zeolitas son su tamaño de poro en el nivel de microporos, lo cual hace que no pues que pueda presentar limitaciones difusionales en el caso de la apertura de estos anillos epoxídicos. Sin embargo, la preparación de estas zeolitas, pues si hablamos de zeolitas sintéticas, podría ser un poco costosa, por lo cual el uso de zeolitas naturales que puedan ser extraídas, pueden reducir costos y además que los usos de este tipo de materiales, o específicamente zeolitas naturales colombianas, son bastante limitados en aplicaciones en química fina. Entonces, en este caso, o como tópico 2, yo les vengo a presentar algunos, digamos, resultados que se han obtenido con materiales mesoestructurados, estos quieren decir los de hierro y cobre, y con zeolitas naturales que se han extraído de fuentes naturales colombianas. Entonces, en el primer caso, nosotros tenemos dos reacciones modelos. Entonces, la idea es abrir este anillo epóxico, cualquier epóxido se puede abrir o se puede isomerizar utilizando cualquier medio ácido, sino que, como les comentaba previamente, lo difícil es controlar la selectividad. Pues en nuestro caso particular es isomerizar estos epóxidos para obtener los aldehídos, los cuales tienen una aplicación bastante importante en la industria de fragancias. Entonces, cuando se incorpora este tipo de sistemas a esta reacción, tanto hierro y cobre, se observa que no hay un efecto significativo, un efecto bastante importante cuando se cambia la cantidad de hierro y cobre, es decir, la cantidad de hierro y cobre solamente cambia la velocidad de reacción, más no cambia la selectividad de estos sistemas, que principalmente que los solventes juegan un rol importante. Los aldehídos se forman bajo un sistema o bajo sistemas apolares. Entre todos los sistemas, independientemente de la cantidad de hierro y cobre, un sistema como hierro soportado a M41 es más activo, con un TON de alrededor de 350, mucho más alto con respecto a sistemas catalíticos previos. Y este sistema es bastante interesante porque es robusto, es decir, se puede reutilizar en muchas ocasiones, y aparte que este sistema no lixivia. Y se obtienen selectividades pues, bastante interesantes, alrededor de 65 para la formación del aldehído a partir del epoxi alfa-pineno y el 99% a partir del epoxi beta-pineno. Entonces, este es un primer caso donde se utilizan materiales mesoestructurados modificados con hierro y con cobre. Pues en el otro lado nosotros tenemos también las zeolitas naturales. Estas zeolitas naturales, ¿de dónde se extraen? Se extraen de Antioquia, de un municipio que se llama La Pintada, perdón. Entonces, de La Pintada se extraen este tipo de zeolitas, son rocas, y luego con una solución de telopolistutato de sodio, lo que se hace es hacer las separaciones de las fases más ricas en zeolitas. Se hace por densidad y luego se extrae la zeolita. Esa zeolita no se calcina porque hay cambios estructurales a partir de 500 grados Celsius, y entonces se utiliza como después del proceso de extracción. A pesar de que estas zeolitas naturales tienen una baja área superficial con respecto a los materiales mesoestructurados, este tipo de sistema y la acidez externa es capaz de isomerizar estos epóxidos. También se encuentra un efecto pronunciado del solvente, sin embargo es menos activa debido a cationes de compensación, pero es menos activa en términos de velocidad de reacción, más no en términos de conversiones o selectividades. Sin embargo, esta zeolita tiende a ser un poco más selectiva hacia el alcohol, hacia los alcoholes de estos epóxidos, y además este sistema es robusto. A pesar de que es un sistema que no se puede calcinar, se puede reutilizar en numerosas ocasiones utilizando simplemente lavado con acetona. Sin embargo, la máxima selectividad que se obtiene es alrededor del 48%. Pero es importante destacar este tipo de zeolitas porque estamos valorizando desde el catalizador, haciendo la extracción de fuentes naturales, hasta la reacción que es la transformación de estos epóxidos que se pueden obtener a partir de la extracción de los aceites esenciales. Entonces, en este sentido, estos sistemas mesoestructurados se pueden modificar tanto con hierro y con cobre. Y la acidez que se encuentra principalmente en este tipo de sistemas, acidez débil tipo Lewis, que favorece la formación de los aldehídos, y además que se tiene una alta área superficial y una cristalinidad bastante alta, que favorece también estas reacciones. Y se obtiene que además que los sistemas de cobre más selectivo que el de hierro. Sin embargo, el cobre, a pesar de que tiene una gran partículas de gran tamaño, se observa una disminución dado esta consecuencia, pues esta partículas de gran tamaño de óxido de cobre sobre los soportes silicios. Que el sistema hierro M51 es un sistema muy activo y que se puede utilizar para la formación de los aldehídos. Es importante destacar que como se utilizan dos soportes silicios, como la M41 y la CBA15, El MSM41 es un sistema mucho más rápido, es capaz de isomerizar con respecto a CBA15 y que una carga baja de hierro hace que el sistema sea bastante promisorio para este tipo de reacciones. Ya en el tercer tópico es combinar laboratorio con cálculos de FT. Entonces, ¿qué es lo que pasa? Nosotros acá requerimos explicar mecanismos de reacción, pero en muchas ocasiones no tenemos las herramientas suficientes para elaborar o por lo menos para determinar los estados de transición y dar una descripción completa de los mecanismos. Entonces, mucha de la literatura se basa solamente en determinar los intermedios de reacción, pero esto no pasa más de ser una ruta de reacción. Entonces, los cálculos de FT o cálculos de química computacional nos permiten a nosotros, en este sentido, determinar las etapas limitantes de la reacción y conectarlo con las etapas experimentales. Entonces, en este caso, no es necesario hacer la simulación de todo un sistema catalítico. Decimos previamente que para este tipo de reacciones el sistema de hierro soportado en MSM41 es un sistema catalítico que es favorable para la formación de este tipo de reacciones. Entonces lo que se hace es simplemente simular la fase activa. Entonces la fase activa es el sistema de hierro y el soporte, que solamente es sílice, no tiene un rol más que depositar el hierro. Entonces, basándose en eso, uno disminuye el nivel de teoría y aparte disminuye el trabajo computacional que se lleva a cabo y se determinan posibles estructuras y estados de transición para la explicación de los posibles productos. Entonces, es bastante interesante porque a partir de la química computacional uno puede determinar el tipo de interacciones no iónicas y covalentes y la estabilidad de los compuestos que se están obteniendo. En este caso particular, nosotros tenemos el epoxi de betapineno, que se puede coordinar al sistema de hierro y forma un estado de transición donde se va rompiendo el enlace carbono-oxígeno y se forma un carbocatión intermediario que se puede arreglar. Y en ese sentido se puede arreglar, ¿por qué? Porque tiene un compuesto interno que es un compuesto bicíclico, pero además tiene varios hidrógenos que pueden sufrir de transferencia interna. Entonces, en ese sentido, la favorabilidad termodinámica acá se hace a la formación de ese compuesto mayoritario que se está obteniendo, que es miltanal, por una simple transferencia de hidrógeno por este estado de transición que se está formando. Y no solamente por eso, sino que las constantes cinéticas revelan que justamente el producto mayoritario no es favorecido termodinámicamente solamente, sino también cinéticamente. Sin embargo, el compuesto que es también isómero, que se llama miltenol, o los alcoholes, no es favorecido con este catalizador, primero por el estado de transición que se está formando, es más difícil transferir este hidrógeno que está en este carbono adyacente al carbocatión que favorecerlo como ocurre en el caso del miltanal, este aldehído, que tiene una distancia menor de enlace con respecto a este estado de transición. Además que la constante cinética es mucho más baja con respecto al estado de transición que favorece la formación de miltanal. Listo, y entonces nosotros, ¿qué estamos haciendo en el CICAT? Entonces, estamos llevando a cabo varias reacciones, y la idea es hacer la transformación de la biomasa con estos monoterpenos. Entonces, actualmente estamos llevando a cabo un trabajo bastante interesante partiendo de monoterpenos como el betapineno. Entonces, estamos haciendo 3 reacciones, 4, pues particularmente. Primero, la condensación con aldehídos para la formación de compuestos isobenzofuranos, que son de especial interés en química médica. La formación de los isómeros a partir del epoxi de betapineno, tanto miltanal, miltenol y alcohol perílico. Estos 3, ¿por qué? Porque el primero de ellos tiene una aplicación importante en la industria de fragancias, el segundo porque puede servir como coadyuvante del biodiesel, y el tercero, alcohol perílico, que sirve como potencial precursor en muchas de enfermedades como el cáncer. Además, también estamos intentando hacer la transformación directa desde el monoterpeno, es decir, desde el betapineno hacia estos compuestos isoméricos del epoxio de betapineno en reacciones one-pot. Y ya el tercer caso es la transformación del isómero del betapineno para obtención de compuestos de alto valor agregado como el limoneno, el canfeno y el afapineno. Y finalmente, esto se apoya a estudios teóricos computacionales, utilizando programas como Gaussian y también Aspen para la simulación de las propiedades termodinámicas, que es de especial interés para observar las variabilidades termodinámicas. Listo, muchas gracias. Ya voy.
Bueno, muchas gracias, Julián, por tu interesante presentación. Abrimos un espacio para preguntas. Si alguien tiene preguntas para Julián. If anybody has questions for Julián.
Sí, hola, ¿sí me escuchan?
Sí, sí, señora, adelante.
Sí, hola, buenas tardes. Hola, Julián.
Hola, Fabio, ¿cómo estás?
Muy bien, ¿y tú? Julián,
Bien, gracias.
respecto a tu presentación, la verdad fue que me encantó, pero fíjate que tengo una, más bien que una duda, una curiosidad. En la diapositiva número 10 tú mencionas que los soportes decorados con hierro y cobre, y mencionas que la diferencia en la actividad se debe solamente al tamaño de los materiales. O sea, ¿en qué estudios realizaron para poder concluir eso?
Hablas con respecto a la diferencia entre hierro y cobre, ¿cierto?
Sí, sí.
Ah, vale, listo. Bueno, eso principalmente porque nosotros probamos diferentes tamaños de partícula, soportando cobre en diferentes tamaños de partícula en los mismos soportes. Entonces nos dábamos cuenta que se había una disminución cuando habían partículas mucho más grandes o cuando eran ya clústeres, es decir, partículas de más de 100 nanómetros. Entonces disminuía bastante la actividad y esto fue, digamos, un argumento para conducir a esa conclusión.
Pero si comparaban partículas de hierro y cobre del mismo tamaño, ¿qué resultados obtenían?
No, es que, bueno, a ver, es que esto es un trabajo que era más de 60 catalizadores, entonces era difícil controlar todo el tamaño de partículas de todos esos tipos de sistemas. Entonces nos enfocamos más hacia la cantidad y ya cuando teníamos dudas particulares del tamaño, entonces sí lo hicimos. Pero sí, como era un gran screening de muchos catalizadores, no fuimos a ese detalle.
Ok, listo. Perfecto. Gracias.
Gracias a ti.
Can I ask a question? On slide 13, you have a set of chemicals. Which product would you like to make out of all of those, or are they all equally valuable?
Julián,
Can you repeat me the question, please?
Sure. On slide 13 of your presentation, you had several chemicals that you were trying to make. Which one of these is the most valuable?
Our articles are available. Yes, you mean that where articles are available? Yes.
No, está preguntando si de todos los productos que mostraste ahí, ¿cuál es el más valioso?
Okay. Okay. Yes. In my experience, the compounds that have more it's more interesting is miltanol, because this is a very important compound in the fragrance industry. So this is a very important compound from the rearrangement or isomerization of beta-pinene epoxide.
What does it smell like?
¿a qué huele, Julián?
¿Cómo huele?
Julián, te preguntan que si, ¿cuál es el
Yes.
olor de...
It's like a pinene. I don't know how to say that because I don't remember what is the word, but it's like a pinene, like a pinene, the clean products that you usually use in your house, or like a fragrances, but I don't remember what is the name in this moment. Y con respecto a la pregunta de Juan Alberto, de la pureza de la ceolita, bueno, a ver, nosotros no hicimos eso. Nosotros simplemente lo que hacíamos es extraer la ceolita en un lote y listo, o sea, preparamos lo suficiente para la extracción, pero claro, puede que no sea totalmente reproducible porque depende mucho también de la zona donde usted vaya a sacar la ceolita. Entonces, digamos que no es totalmente, no se garantiza totalmente la reproducibilidad porque los traemos de una roca específica, pero queda abierto, digamos, a continuar con ese estudio. ¿Y cómo afecta la selectividad cuando hace la POT? Bueno, principalmente afecta el tipo de agente oxidante que usted vaya a utilizar y también el tipo de acidez, porque usted debe tener en estas reacciones un carácter metal ácido, metal para la formación del epoxio y carácter ácido para la isomerización del epoxio, la isomerización del epoxio, que es lo que muestro acá al final. Entonces, esa etapa, la primera etapa de epoxidación, se requiere un catalizador metálico, mientras que en la segunda etapa requiere un catalizador ácido. Entonces, la selectividad principalmente sea por el carácter metal ácido del sistema y el agente oxidante que se utiliza en la primera etapa para la formación del epoxio.
Bueno, muchas gracias. Si alguien más tiene una pregunta para Julián. No, bueno, entonces continuamos. Let's continue with presentation of Professor Dauenhauer with catalytic mechanics of dynamic surfaces.
So just a short presentation of Paul Dauenhauer. He has very recently been declared a genuine genius after receiving the MacArthur Fellowship, if that is all right, Paul, that assessment, okay? So this is a very important award that is conferred in the US. Also, he has many works that have more than, I think that around 10,000 citations on Google Scholar. So he has had a very prolific scientific life, because according to his biography, he received his PhD in 2008. So that's a very impressive list of achievements for such a short time. Just as a reference, I received my PhD in 2009, and I have received, let's see, 0 prizes so far. So, so thank you, Paul, for participating in our seminar. He was very kind to accept my invitation via Twitter, where he is an influencer actually for the catalytic community. And it's a pleasure to me to introduce him and to welcome you to our activity, and the floor is yours. Your audio is, we cannot hear you.
You are mute.
Yeah, you're mute right now.
Okay, how is that? Is that?
Yeah, that is perfect.
Okay. Okay, so I'm going to move this so I can see you all at the same time. Okay, so thank you for the invitation. So it's a pleasure to introduce you. I do research in the field of catalysis, but I'm more in the field of catalysis and reaction engineering together. And my research covers essentially 3 areas. One area is renewable chemicals from biomass, the topic that we were just talking about. Another area is pyrolysis of biomass and plastic materials. And the third area is what I'm going to talk to you about today. It's our newest research focus area, and we've been moving very quickly in the past 2 years on this new idea. I'll set up the problem and kind of give you some examples as I proceed. So if you've never been to Minnesota or seen Minnesota, we're one of the 50 states in the United States. We're far up north. This is the border of Canada right here. This is Wisconsin, North Dakota, South Dakota. Chicago is down here. Let me see if I can get my, I don't see how to do it. The problem in the United States and around the world is that people mostly live in cities. This is the Minneapolis-St. Paul city right here. And more than half of the people in the country live in this city. At the same time, we have a lot of wind power, wind turbines in the country, but also in Minnesota, and that's way down here. You can see this is the wind speed. And so there's a big distance between where we can produce renewable energy and where we can use it. And so the problem becomes, how do we deal with this problem, not only in Minnesota, but in the United States, but also in the world? The same thing goes for Asia, where a lot of people live in India, China, Japan, and there's a lot of solar power available, but it's in Australia. And there's been this idea for a long time that we could take solar power and wind power, turn it into hydrogen using electrolysis, and then turn that hydrogen into ammonia. And once we have ammonia, it's liquefiable just like propane, and we can put it in a ship and we can move it around and sell it, trade it, store it. We can make it in the summer, use it in the winter. We can make it during the day or at night and use it during the day. We can trade it and sell it where it's needed, like a commodity. And so this is very appealing because ammonia doesn't emit any carbon. It would be a carbon-free fuel that allows us to make wind and solar at a large scale, or fusion technology as well. And it would allow us to use baseline power the way we do now without emitting any carbon. So this is a dream technology if we can do it. Of course, we know how to do ammonia synthesis right now. We know how to do electrolysis right now, but they're not cost effective. They just cost too much. So why is it too expensive to do ammonia synthesis on small scale and distributed systems? It all comes down to the thermodynamics. And if you look at this reaction, you have to break apart N2, and then you have to add hydrogen to that nitrogen atom to get ammonia. And this is the thermodynamics. So this is the mole percent of ammonia that you would make at two different pressures, high pressure and low pressure, and the temperature right here. Now, for this reaction to proceed, you have to break apart N2. And so the reaction temperature has to be up here in 400 to 500 degrees C, where you only get conversion at 100 atmospheres roughly of only about 20 to 30%. So what we would like is a faster catalyst. If we could speed up the catalyst, we could operate it at lower temperature, and we could operate down here in the 200 to 300 degree range, and we could get higher conversion. So why can't we make a faster catalyst? This is one of the oldest catalytic chemistries that exists. If we could make a faster catalyst, this would address this problem, but it would also address many other problems because it's the origin of the problem has to do with the fundamentals of catalysis. So if we think of a general picture, we have some reactant and we have some product. Can you see my mouse okay? My cursor?
Yes.
Okay. Okay. So in a gas phase reaction, we would proceed through some large barrier. And the idea of a catalyst in general is that on a surface, we can lower the barrier. This is what we teach undergraduate students. The problem is that when we have a reaction on a surface, we introduce another barrier, at least one more, which is the heat of adsorption. And so this barrier here, presumably, we would like to be comparable to the heat of adsorption so that this is not rate limiting, right? And I can imagine different materials that change the ratio of these two. Now, if I would like to speed this catalyst up even further, what I could do is think about changing the surface thermodynamics of this molecule and this one. And if I make this more exothermic, I will lower this barrier right here by the BEP, the linear scaling relationship between the surface energy and the transition state energy. And so this reaction will go faster. The problem is there's always a trade-off. If I make this reaction faster, I make this reaction slower. And so at some point, I can no longer speed up the overall reaction because I've balanced the two reactions, or the two steps, in this case, of desorption and reaction to the point where they're maximized. Now, this simple idea is the core problem in a lot of catalytic reactions. If I take a bunch of different materials, they all have adsorption, reaction, and desorption, and different metals or metal oxides will have different parameters here. This is just a characteristic of that material. In ammonia, the materials that exhibit this maximum are iron and ruthenium, and other metals are either reaction controlled or desorption controlled, or ammonia converted, or the surface reaction controlled. So the problem is I would like a reaction that exists up here, orders of magnitude 10, 100, 1,000 times faster, and there's just no way to do it. I can't make a material that's faster for each of the steps independently. So this is a very old problem, and it's something that's been discussed for decades and decades. How can we beat this problem? And I have not seen a significant breakthrough in how to do this yet, and it's something I've been thinking about for a decade. So let me propose a very simple idea. If I take the reaction, I can proceed under a metal or metal oxide to adsorb on a surface. I can react to make a product. Now, under this condition, the barrier to desorb from that surface is too high. So what I'm going to do is I'm going to take my catalyst and I'm going to change it so that I change from state 1 to state 2. And when I change from state 1 to state 2, now this molecule can go up to point B in the gas phase. And then the material can flip back to state 1 and reload my surface. And I can keep flipping back and forth between these two states to not only increase the rate of the surface reaction, but also increase the rate of desorption simultaneously. This is a simple idea I'm going to talk about now for the rest of the presentation. So if I think about it this way, I have a rate control in the reaction, which continues to increase independently of everything else. And I have a rate of desorption, which also increases independent of everything else. So if I'm doing each of these two steps independently, and I'm switching back and forth between them, the best I could ever do would be the condition here and there for this given amplitude and the shift of that particular material. And what you can see is if I'm able to change a material back and forth, back and forth, back and forth, I am now not a little bit faster, I'm orders of magnitude faster, right? 1,000 times faster just by changing a material on the speed at which is required to get up to this condition right there. So the question is, does this work and can we do it? Well, let me start with the first question. What I'm going to do is I'm going to take a very simple generic system. I'm going to take molecule A and I'm going to make molecule B right here in a perfectly mixed reactor. I'm going to keep it really simple in terms of the chemistry. I'm going to put some catalyst into this. I'm going to have a reactor space velocity, temperature, pressure. I'm going to have the normal catalytic chemistry parameters, but now I'm going to have new parameters. I'm going to have the frequency at which I'm changing that surface. I'm going to have the amplitude of binding energy, how strong, and then how weak, and then how strong, and then how weak I'm changing it. The position of that, so I can slide my amplitude left and right, but keep the same total amplitude and oscillation. And then the waveform type. Is it a sinusoidal wave? Is it a square wave? Or some trigonal wave? Or something more complicated? So here's what a simulation looks like. And the place to start thinking here is the relative binding energy. So I'm binding strongly, weakly, strongly, weakly, strongly, weakly. And every time my catalyst goes from strong to weak binding, the reaction rate, this is the reaction rate right here, goes up really high and then comes back down. And then it goes up high again and comes back down. And here is my surface coverage. So every time I'm flipping back and forth, my surface goes from covered in A to covered in B. You can see it goes to a completely covered to completely uncovered in A, back and forth. So my material is just constantly switching between two different states all the time. Now the question is, how fast should I be switching between these two states, right? Back and forth, back and forth. And so what I can plot for you is my instantaneous turnover frequency. This is the reaction at any specific moment in time. And I can do this now for different frequencies. So here's very slow up to very fast. This is the best I can do without any sort of changes, just a static maximum, the peak of the volcano plot. And you can see that when I get up to 0.25 hertz, I'm now matching that. And if I go faster in speed, I'm considerably higher. I'm at least an order of magnitude and almost 2 orders of magnitude faster just by working at 1,000 hertz. So I'm switching that surface 1,000 times per second. Now I can do this with even more frequencies, and I can make a plot that looks like this. So down here on the bottom, this is the frequency at which I'm switching the surface between two states: weak binding, strong binding, weak binding, strong binding. This is once per second right there. This is 10 times or 100 times per second, etc. Right? And what you see is that this right here is the best I could do for a normal catalyst. But my dynamic catalyst, the catalyst switching with time, just continues to increase linearly between the two. And it goes up to this point right there, where no matter how much faster I flip the surface back and forth, I can't make the reaction go any faster. So this point right here, the one you see there, I go back, is this point right there. You can see that. I can't go any faster because the independent steps on their own cannot go any faster. Okay. And this will hold until the point where I can't fill and unfill the surface fast enough, and then my rate will drop. So the question is, how fast can I go? And so what I'm showing you now is this is the frequency at which I'm switching my surface. This is how big of an amplitude switch, how strong and weak I'm making it. And then this is the rate of reaction here averaged. So you can see I was showing you an oscillation amplitude before of 0.6. So you can see it went up, plateaued, and then it came back down at the high frequencies. But what you can see is even in this resonance condition here, if I had gone to higher amplitudes, I would have gone considerably faster. You can see this is 1,000 turnovers per second for a catalyst, which is incredibly fast and probably going to be diffusion limited before I would even be able to achieve a reaction rate that fast. So the question is this a good idea? Of course, if I put in all this energy to drive a system back and forth and back and forth and back and forth, do I get a benefit out of that, or am I spending a lot of energy I don't use? And so a very simple idea is this idea of a turnover efficiency. And it's very simple in nature. This is my dynamic reaction rate. And so how fast is my reaction rate compared to how fast I'm switching my surface? And I subtract off the steady conditions to figure out if I'm really improving or not. So what you see is that there's a range in here where I'm incredibly efficient. In fact, I can turn over the reaction 1 time per second in this region right here, that you see in dark red. So every time I flip over the surface, it's actually flipping over the reaction. And this region right here, if I back up a little bit, is this region you see right there. Every time I increase the rate at which I'm flipping over a surface, I'm increasing the reaction rate. And eventually, once I get to here, I know no matter how fast I flip the surface, I can't increase the rate. Therefore, my reaction rate drops at high frequency. So this system can be very efficient, but only under specific conditions. So the question now is, this is an example of a simulation. Can I take this and apply it to hundreds of different reactions? And to do that, we need to generalize the chemistry. So I think about a surface reaction. I think about a molecule on a surface forming another molecule on a surface that goes through a transition state. And the relationship between that is linear. So A goes to B. That scales linearly by this linear relationship with parameter alpha for the slope and beta for the offset. And so as I change alpha, I'm going to change the slope of this reaction line. And my volcano is going to go from very steep to very broad. You can see what happens then is my inverted volcano actually also gets very wide. So different chemistries will have different parameters, and they'll have different shaped volcano plots. Now, the effect of that for dynamics is really important, because if I think about the shape of this volcano plot, that determines what conditions I can do up above in the inverted volcano. So what you're looking at here is a volcano system with an alpha of 1.0. This is the amplitude from 0.6 up to 1.5, just enormous amplitudes, right? These are probably not realizable in any way. The 0.6 to 1 might be, 1.5 is just extreme. But what you're seeing is this would, if it was possible to do this, it's not, because it's too fast, you're getting close to 1 million turnovers per second at these conditions. And you can see now I still get a resonance band, and as I increase the amplitude, I get faster and faster and faster. So an alpha of 1 is a very steep volcano. Now if I change this, now the alpha is 0.4. You can see that, and what happens is my volcano gets a lot shallower. And so when I do that, I can't use higher amplitudes to get me up to the same high frequencies. In fact, as the volcano gets shallower, my effect of increasing the amplitude decreases significantly. So if I'm going to pick a catalytic system, I would like to design one with a surface and a chemistry that has as steep of a volcano as possible, so as high of an alpha value as I can find. Okay, I'd like to generalize this further, though. For any reaction, even for one as simple as this, there are more parameters. So I have A in the gas phase, B in the gas phase, A on the surface to B star, that's determined by this transition state, and those are the parameters I was just talking about. So alpha and beta are the scaling relationship by the slope and the offset for that transition state. But there's another parameter which matters a lot, which is if I'm changing something like B star in energy, then A star will also change in energy. The question is, how much will they change relative to each other? And there's another linear relationship there that describes how these two energies of the adsorbates change. And we're going to describe that linearly with slope gamma and offset delta. And that allows us to completely define our entire system with these four parameters plus the heat of reaction. Now there's one more point that matters here. Gamma is the slope of how much they change. Delta is the point where they're equal in energy. So you can see here the delta point is where as we change the binding energy, those two are completely equal. Now, as we switch the values here, just the shape of the volcano we're working with changes. You can see that at a point of 1 where the two are equal, that means the two molecules on the surface move up and down together. Okay, and you can see that that's the point right here in black. And the problem there is, as I'm changing the binding energy, the surface intermediates move together, and I don't change the transition state energy at all, which is, of course, my goal. So I don't want to have any of the values of gamma close to 1. I want to be able to manipulate the molecules on a surface in favorable and unfavorable ways. So I want to stay away from this quantity here of gamma of 1. Now I can imagine these systems visually, and this becomes more important as you get to more complicated systems. So here's the heat of adsorption of the surface reactant. Here's the heat of adsorption of the surface product. And there's a linear relationship between the two, defined by the slope gamma, and there's a point where they're equal in energy, which is our delta point. Now, what's nice about this is that it allows me to visually interpret what's happening on a surface, but I can also apply it to a real system. So if I'm going to go back to ammonia, I care about the reaction to make NH3 through N by adding hydrogen. So here's NH star with 1 hydrogen, here's NH2 with 2 hydrogens. These are calculated values on different materials, so rhenium, platinum, gold, and you can see that they change in binding energy, but the slope between them is 0.5. It's low. But if I look at something like NH star and NH3, now my slope is even smaller. It's a slope of 0.2. So my ammonia binding energy changes only a tiny bit for how much my NH star binding energy changes, which makes a lot of sense because of the coordination of those molecules by themselves. Now you're probably looking at this and saying, well, you know, these are different materials. Of course, their binding energies are quite different, right? To do what I'm saying, I would need to put in one metal and then put in another metal and then put in another metal and just swap metals out 1,000 times per second, which is, of course, is impossible to actually do. So the question becomes, is this possible to do experimentally? And so this is an idea I've been working on for the last, let's see, it came out just recently. So I've been working on this since January, which is a new article, actually just came out in ACS Catalysis. You can read about it, where we've described 10 different ways where we can manipulate the surface adsorption enthalpy of reactants. And these include things like surface strain, variation of a surface pocket, or a surface pore, a surface pocket, plasmonics of surfaces with using light. This is a ferroelectric material here, which imposes an electric field on a surface. This is a backgated system. This is surface acoustic waves. This is a solid electrolyte, a Schottky junction, or just electrocatalysis. So if you're interested in doing this for a different chemistry, you can actually read about this paper right here or in the paper that's in ACS Catalysis. The idea, though, is that these kinds of changes are possible in real systems. Let me give you an example here. This is, oh, is there a question? Oh, okay, so this is a system here, I believe it's on platinum, where we've taken methane, hydrogen, formaldehyde, and compared its binding energy to methanol. And what I'm doing is I'm changing the electric field that molecule sees on the surface. So again, you're seeing for methane, I'm seeing very shallow gamma values. It's a very slight slope, which makes sense because methane does not interact with the surface very strongly. Hydrogen does more strongly, but it's still relatively shallow slope. What's interesting about methanol versus formaldehyde is that it actually has a negative slope. One of the molecules binds stronger, and the other one actually weakens as the other one binds stronger. It's a very unique system. If I look at another mechanism, this over here on the right, this is surface strain. So I'm going to take a metal and I'm going to pull it apart and I'm going to push it together. Okay. So what you see, this is the difference between oxygen and carbon monoxide. And all the different metals give very different slopes for that type of variation in the strain of that particular surface. But you can see here for these types of levels of strain, we're getting about 1/4 of an electron volt. So about 25 kilojoules per mole in binding energy shift. Let me give you an example of a paper that I wrote recently with my collaborator, Professor Omar Abdelrahman at the University of Massachusetts. And this was an example of this dynamic concept that we started working on about a year ago. And the idea is very simple. We take formic acid, we let this react to make carbon monoxide, and then we switch the voltage at the surface to undergo electrooxidation of CO to make CO2. And we just switch back and forth between open potential, 0 volts, and 0.8 volts. And so what we see is this is the applied potential on a surface, and this is the rate of reaction right there to make CO2. So if I just fix the voltage at one particular voltage, I can actually do this many times, and I can see that the maximum rate I can get is right here at this peak. So that's the fastest we could ever go. If I'd gone up higher in voltage, it would have actually slowed it down. Now what I can do instead is oscillate between one side versus the other, and I can push this rate up over an order of magnitude 20 times faster by oscillating between 0.8 and 0 at 100 hertz. So 100 times per second, we're switching the potential of that surface. This is actually experimental data right here where we measure the rate of CO2 formation. So this is our first example that this can be done. This is another paper we just wrote where my collaborator was Phil Christopher. He actually led the work on this, where we took particles of platinum and we took methanol and we decomposed methanol to make CO, carbon monoxide. And then we pulse this with light, weaken the binding energy, and remove CO. And you can see here, light is very different because what we can do is selectively excite different molecules. This is the binding energy of the molecule versus the intensity of the light that's been exposed to it. So you can see that NO has almost no change in the binding energy with an experimental error, whereas carbon monoxide changes by almost 1/4 of electron volt under different intensities of light. So these are 2 experimental examples to show that these types of behaviors are possible in real systems. Okay, so the idea of accelerating a reaction is very exciting, right? Because we can achieve rates that have never before been possible if we've only taken a catalyst design approach. But there's more things we can do with these types of reaction systems, these dynamic catalytic reactors. And that has to do with the other problem we have in many systems, which is equilibrium. So if I take the ammonia reaction system, this is my equilibrium conversion. So if I let the reactor run for a very long period of time, and I change the temperature down here, what you'll see is what I talked about earlier. As we get to higher and higher temperature, right up here in this range, I'm only getting 20–30% conversion. Other reactions have the same problem, like the water gas shift reaction or a methanation reaction here, or driver forming of methane. This should be methane right there, to make CO and H2. Now, how do we normally deal with this as catalytic reaction engineers? Is we take a reaction of interest, we change the temperature, we change the pressure, we change the concentration until the reaction is favorably equal by equilibrium. Now that's a problem because once we do that, we fix the conditions that the catalyst has to operate at. And that's what we see with ammonia. We have to operate ammonia synthesis at high temperature, but that's actually driven by the catalyst. But then the equilibrium is really bad. So what we would like to do is run a reaction under conditions favorable for equilibrium, but also favorable for the catalyst at the same time. And we can do that by the fact that we're actually manipulating the surface, which adds in work to the particular system. So here for a system, I haven't changed the equilibrium of the reaction, but because I add in some amount of work, some added Gibbs free energy, I can change the steady state of my system without changing the equilibrium. And this is great because it gives us the freedom to use a catalyst at many different conditions, independent of how the catalyst is going to operate. So let me give you an idea of how this works. Let me back up. So here's a simulation we've done where we say we take a batch reactor, we put in molecule A. This is, again, the same type of system we worked with before. So here's our mole fraction of starting material. Here's pure component B. Here's pure component A, and everything in between. So my starting conditions can be any possible starting point that I'm interested in. And I let that batch reactor run on a catalyst for any amount of time that I want, just up here, 200 seconds time on stream. And I'm applying a square wave at 1,000 hertz. And my amplitude here is relatively small. It's only about 20 kilojoules per mole. And what you see is my reaction doesn't actually go to equilibrium. It goes to equilibrium plus an offset to this new steady state that you see up here. And what happens is if I turn off the dynamics and go back to a static system, it comes right back to equilibrium as it has to, or else we're violating some thermodynamic laws. So why is this happening, right? This is very unnatural for a catalytic system. And if I think about this, what's really going on is as I'm moving the surface up and down, I'm actually adding in the work to take something from weak to strong binding. And so under one condition, the molecule in green here goes to yellow right there, okay? And then once it goes to weak binding, it can desorb, but it doesn't go backwards. So this work we're putting in is actually favoring a direction, either forward or backwards. The question is, how effective is it at doing this? There's an actual efficiency to how much work I put in this change in the oscillation amplitude to the free energy of what's actually changing. Now, I can actually explore this very idea very simply. I'm going to take a system. This is my static volcano curve right here. This is my turnover frequency to make a product, and I'm going to take this system and apply an oscillation amplitude. You can see here, the amplitude is not listed, but I think it's about 0.6 electron volts. And I'm going to move that amplitude left to right. So I'm going to fix the total amplitude, but move it side to side. So you can see that there's a condition here where the two are matched in oscillation frequency, and then this goes up, and this one here comes down. Now, as I do that for this batch reactor, what I want to ask is, if I let it run for a very long time, what state does it go to? Does it go to equilibrium? Does it go to higher conversion, or does it go to low conversion? So what you're looking at here is this shift in the oscillation amplitude from left to right, down here at the bottom. Here is the oscillation frequency. So this is faster. This is 1 hertz. This is 10 hertz. The system will naturally go to equilibrium under normal static conditions. So that's in the green here. So at very slow conditions, the reaction just goes to equilibrium. Now, as I get faster and faster, the reaction will both go forward here in red, but it can also go backwards. So I can force it backwards or forwards depending on the conditions that I pick. And there's actually a very clean division between what's forward and what's backwards for this ratchet system. Now, what do I mean by that? Why would a reaction go forward sometimes and backwards another away from equilibrium? And so we can imagine kind of two scenarios here. One is I'll take the forward direction first. This is the strong binding condition. And what you see is as the reaction proceeds, it goes down into the strong binding state right there. And then as I go to weak binding, this molecule can desorb in the forward direction, but it's hard to go backwards. Okay. Let's take a look at the reverse case. Now, in this case, I'm going to fill this strong binding condition. And then when I go to a weak binding condition, this is going to go into the gas phase. So the clear division here is the difference in binding energy between this state and that one. When this is lower in energy, the reaction goes backwards. When this reaction here is lower in energy, we go forwards. And so what's happening right here, this is the point, the delta point, where these two are exactly equal in energy. And that's where I decide if I'm going forward or backwards for any system. So then the question becomes, how efficient are these systems? Well, obviously, it depends on the shape of how that surface is moving. So I can look at this reaction system here as the amount of change that I see versus how much effort I put into it with an amplitude. But I can also ask this in terms of the shape of the waveform of how the surface is changing. So I can have a sinusoidal wave, I could have a triangular wave or a square wave or some more complicated system. And what we found throughout the research is that square waves are significantly more efficient than sinusoidal waves and more efficient than triangular waves. Okay, well, let me leave you with kind of one last idea that we've been pursuing, which is normally I work with systems that are more complicated than a singular elementary reaction. And for the most part in catalysis, a lot of times we're very interested in selectivity control versus rate control or equilibrium shifting. So if I have a reaction that goes A to B and A to C, can I use dynamics to tune a reaction to one pathway or the other? And so let's take a system that looks like this. And you can see that one of them has a low gamma, a shallow slope, and one of them has a high gamma in terms of how they change their surface binding energies. And you can see here, these are their two dynamic energy diagrams for the two different pathways. Now, if I'm thinking about the rate of reaction to these, you can see that under most conditions for binding energy here, in other words, if you think about this, if I take a bunch of different metals, almost all metals, or a large number of them, will easily make product C, right? It's very easy to make product C. It's hard to make product B purely. In fact, under these conditions over here, I only get about 50-50 of the selectivity to B as the best I could ever do. So my question is, can I make a system that's dynamic that accelerates the reaction in red over the rate of reaction in blue? And you can see here, this is a simulation series we've run where we take the oscillation of the surface and we take the oscillation amplitude and we shift it again left to right. And what you see is what emerges in this range over here, what you see right here, is this region starting at about 1 hertz where the reaction becomes perfectly selective to product B, even though it's not normally possible to be selective at all. Now what's happening right there is this amplitude here, I'm shifting it over, it's flipping between either side of this volcano, and it's accelerating this reaction above the reaction in blue. So you can see here, this is the rate of conversion of the reactant. You can see it's fast here, and it's fast there. This is the same independent axis. The x-axis here is the same for all of these, and the vertical axis is the same for all of these, but now I can compare them and see what is related to what. So this is where A is fast converted. This is where A is fast converted. This point here goes with the acceleration to make B, and this is where I get high selectivity to B and low selectivity to B as well. The fast selectivity to A comes when I accelerate it over the peak of the A volcano, or the C volcano, right? This point right here, if I back up, corresponds to this region right up here. So it's possible to use dynamic surfaces that change in binding energy or shape, so you're changing the enthalpy or the entropy of the surface by using complex or simple waveforms or even more complex waveforms. And we've talked in this simulation series about A to B reversibly. But what happens when we go to more complicated systems? We now have the dynamics of A to B, B to C, and C to D. We have parallel systems of E and F. We have bimolecular systems. We have complex mechanisms like Ely-Riddell, or we have in systems like bizarre dynamics where one molecule binds stronger and the other one binds weaker. And so one of the things we're doing is looking at the kind of the theory of how these systems change under dynamic surfaces. Are there ways to tune and control them? And more importantly, are there basic principles that we can pull out to understand and think about more complicated systems without just running thousands and thousands of expensive simulations? Of course, the other thing we're doing at the same time is saying, can we take these basic ideas and use them in real chemistries? And so I've showed you one for dynamic electrocatalysis. I also showed you one for dynamic light photocatalysis. But we're also doing these with other forms of dynamic electronic systems that are currently under experimental trials. So we have a lot of people at the University of Minnesota working on this. This is me right here. I work on the experimental part of dynamics, and all the simulations you've seen here also come from me. My collaborator that did the electrocatalysis work is here. I'm actually missing Phil from this picture, but Turan Birol helped me understand how materials behave under dynamic oscillations. Dan Frisbee and I work together on electronic systems, and she and I work on optimization, and Professor Velakos at the University of Delaware works on dynamic oscillations. So let me just end it here. It's a short presentation, but there's a lot of material. So let me just summarize quickly. I think there's enormous potential in being able to control the surface of a catalyst with time on the time scale of a turnover frequency. So people have talked before about changes that happen over hours or days or years. I want to take a catalyst and I want to purposely change it on the time scale of milliseconds. one state to another state on the time scale that we would turn over a reaction. If we can do that, and we do it in the right way, we pick the frequency, the amplitude, the waveform, we can accelerate reactions orders of magnitude. But we can also take those systems and make them selective. And not just a little bit better and selective, we can make them perfectly selective, like an enzyme does. We can say, how can we get to 99.999% selectivity by driving the desired reaction thousands and thousands of times faster than the parallel chemistries? But of course, there's just decades of work here to do. To understand the basic theory of and fundamentals of how these dynamic systems work, to make materials that can change with time, but also to understand what's happening at kilohertz conditions. So this is not my group. I'm part of a U.S. Department of Energy Research Center that's led by Professor Dion Velakos at the University of Delaware. This is me here standing in the back. This is my student, Christine. And my other student, Katie, is here as well. But here's Omar Abdulrahman, who did the electrocatalysis work. Oh, here's Katie, my other student. So thank you very much. And let me know if there are any questions.
Well, thank you very much for your presentation, Professor Dauenhauer. It's really deep, the understanding of the functioning of catalysts. Well, I have a question, but first, if somebody else has questions.
So, thank you, Paul, for such a wonderful presentation and very interesting new concepts, actually. Alejandro Karlovic from Universidad de Concepción had to exit the presentation, but he was talking to me apart and saying that this is impressive. So congratulations on such a beautiful work. I have maybe some questions which are very basic, and one of them concerns the experiments. I mean, how do you set up these kind of experiments?
Yeah. So first of all, I just want to make sure the students understand this is very ambitious, right? In the sense that this might almost be impossible, right? We have a few examples of it like this, but I think what you're asking, Victor, is the perfect question, right? Because we don't want to study a lot of, years and years of theory for something that's not possible. So what are the ways we're going to be able to do it, right? Let me give you a couple examples. Surface strain is an area that's been heavily studied. If I take a material and I strain it, I pull the atoms apart, and that changes the overlap of the orbitals between the metal atoms, and that changes the binding energy. Now, there are lots of ways to strain a surface. One is to use this intercalation approach, where we intercalate small ions like sodium or lithium into a material, and when we do that, they'll pull together and have stress between the atoms, or as we pull them out, they'll actually pull apart. You can also do this with waves. So if you take a surface and you have Rayleigh waves on the surface, that strain from the curvature of the surface will change the binding energy. This is the area I'm working on at the University of Minnesota, and I haven't published on this yet, but we're working on it. If I take a catalytic layer right here, and I put a dielectric here, so it's not an insulator, but it's a semiconductor, and then on the bottom I put another metal, what I can do is I can apply a voltage. And what that does is it puts a counter voltage into the metal. So what you're really doing is you're moving the Fermi level up and down of the metal with time. So I make a metal, more electron rich, more hole rich, electron rich, and I can do that at megahertz frequencies. This has actually already been done under static conditions. This is essentially a MOSFET or a transistor, right? But I want to take that transistor idea, and my colleague Dan Frisbee actually came up with this, and use that to tune the electronics of a metal or metal oxide with time. Now, once we've shown this under static conditions, we're trying to show it under dynamic conditions. Once we're able to do this with one material, you could do this for hundreds of materials, thousands of materials, as long as you understand the type of selection of materials, the synthesis, and the relationship between the applied voltage and how much electron density we can vary in the material. Now, these other techniques here, like ferroelectrics or Schottky junctions, are actually very similar. They're just done by different methods, right? So this kind of space right here all plays around with the idea of I'm going to change the electron density of a metal or metal oxide. And I can send you lots of papers on this. There are examples of this being done right now.
Okay. And another question is, okay, so if I understand well, this catalyst also have to be the catalyst somehow needs to be redesigned with this technique. So I was thinking, because we normally work with catalysts in the forms of powder, and many of them are actually non-conductive powders in which you simply have some nanoparticles spread over the oxide. So the design of the catalyst, now that you explain it, has to be completely different for this kind of approach. Or am I?
For some systems, yes, because this one here is more like a device, like you'd have a microchip, right? So that's going to be more expensive to fabricate. The question is, for this type of approach, is that what you're going to want in the end, right? For an approach like this one right here, this is a photocatalysis approach, and there are ways to scale up photocatalytic reactions. Same thing for dynamic electrocatalysis. There are a lot of ideas on how to scale electrocatalysis systems to larger, when you keep the price reasonable. But what the good thing is here, if you can go 10 or 100 or even 1,000 times faster, the size of your system gets a lot smaller. And it's possible that that benefit of scaling down the system, saves you enough money that it makes sense to do more complicated synthetic techniques like this. But again, so the students understand, this is ambitious, but I'm in my 10th year, 11th year as a professor, so I wanted to go after something really big. And but at the same time, we can't move too quickly. You have to move stepwise and methodically and show that what we're doing makes sense along the way.
I have a question that is asked via written questions. So somebody asked, Cesar Patiño, actually from Copetrol, have you think about combining this kind of catalytic approach with some geothermal renewable energy options?
So you mean like taking focused sunlight or something like that?
Yes, like
so just
it's a difficult question.
Okay, so my big interest here is, can we use these for electrolysis and for ammonia synthesis? So in that regard, it's in terms of systems, it's applying things, putting them together, right? There's a whole other area of reaction dynamics that are not catalyst dynamics, but reactor dynamics. So, and this has been studied for 50 years. Can I take a reactor and I can change the temperature with time, or can I change the pressure with time, or can I flow this way, then that way, then this way, then this way, right? That's another area of research, but there's been a lot of work done on it that says there's some very interesting phenomena that can come about. I think they're very different in terms of what they can achieve, though, right? So changing the catalyst or changing the reactor can give you very significantly different benefits, and that's why I'm very focused on the catalyst.
Well, I'm going to ask a final question in my case, to leave some room for other questions.
Sure.
When you could you expand on this concept? I don't remember the number of the slide in which you show that you are moving between the equilibrium and then in another position. This plot, could you a little bit expand more?
Sure.
The next one, 32. I think I think the one before, where you had the dynamic mode and the static mode. This one.
Yeah.
Could you?
Sure. So these systems, I use the word ratchet, and the word ratchet is a concept of an asymmetry in the profile. For in this case, I'll come back to this right here. This, you can see there's an asymmetry here, right? Because it's different on the left side and the right side. This has been used to force systems forward and backwards. And I'll give you an example. In your body, in the cell wall, are things like ion pumps. So in the cells in your body, you have sodium, you have calcium, and your body wants to move those around outside of equilibrium. So it uses this idea of a ratchet to force sodium one way and force calcium the other way. And that creates this asymmetry and also a driving force away from equilibrium. Now your body uses ATP, your energy source, to do this. We're using something like electricity or strain or force or something like that. Now what we're using this energy input is to drive it away from equilibrium. And so when we look at this simulation right here, the difference between equilibrium and steady state has to do with how efficient the system is, but also the amplitude that I'm picking right here. Now, if I had picked different conditions, I could have driven it to, I could have driven this down, I could have driven it up. But the fact that I picked a relatively small amplitude means that this offset was small. Now, this is very unsettling because we always tell undergraduates in catalysis and reaction engineering that reactions always go to equilibrium and that the catalyst never changes equilibrium. So this is, if you're teaching an undergraduate student, I would never tell them this because it's too confusing for them, okay? But the truth is, if you take a catalyst and you apply work through it, then the catalyst itself can manipulate the steady state away from equilibrium. This is not controversial in biology. In our field of metals and metal oxide catalysts, this is very controversial. But conceptually, in terms of the physics, it's not controversial at all. It's just that we haven't shown it yet experimentally. I don't know, is that the kind of what you were asking about?
Yeah, okay, thank you very much.
Sure.
But, by the way, there is a lot of undergrads in the audience.
A lot of what?
A lot of what? Of undergraduate students.
Oh, okay. Uh-oh. Okay, well.
Well, continue with the questions from other people.
I'd like to ask a question.
Yes.
Professor, myself, I am a student of chemical engineering, but I am a undergrad student as well, just as Professor Victor said. And I am barely starting to study the basics of catalysis. In my case, I am barely starting to study the adsorption properties and basic equations like the Langmuir isotherm and those kind of things. So, well, the general idea of a catalyst is that you can lower the activation energy of a certain reaction, and hence it may be less expensive in the industrial scale, or it will be simpler to occur. So that's a good thing, but there then occurs a little problem, let's say, which is the adsorption heat. Yeah, after you explained that part at the very beginning, you said something about you can make a material to be designed for a specific part of a reaction. What did you mean with that?
Yeah. So if I think about a system like this, I can try to tune a reaction to be more favorable for one part or the other. Think of it like a contest, right? I can either improve this step right here, or I can improve that one. But at some point, I can't improve one without taking from the other, right? It's a trade-off. So if I increase this rate by dropping this barrier, I can do that by lowering this energy right there, right? So as that lowers and gets more exothermic, this barrier will drop and it'll happen faster. But the trade-off is that this desorption barrier here, it's really high. So if I was to decrease that desorption barrier and raise this up, now this rate here slows down. So by increasing one step or the other, I have this trade-off that I can't beat. And that's why if I go forward a step, I can never go any faster than this point right there. Think of like a series of things that have to happen, right? Step 1, step 2, step 3, step 4. I can never go faster than the slowest possible step. Although I can tune things so that maybe 2 of the steps are about the same speed, right?
Okay, thank you. And I'd like to ask a little something. You said in the very beginning that you also have researched something about pyrolysis of plastics. I know this is not that topic, but in general words, this is meant to be some kind of, let's say, green investigation, or in order to reduce the pollution or the contamination.
So I work in the area of polyethylene and polypropylene pyrolysis. So plastics that we use for, well, they're everywhere, for food wrapping and things like that. Those are the largest by volume plastics on the planet, and they don't biodegrade. So we can take those, we can break them apart using thermal energy and get back ethylene and propylene. And that's a closed cycle. I take ethylene and propylene, I make the plastic, I recollect the ethylene and propylene, I use the plastic. But because I get the ethylene and propylene back, the plastic I remake every time is just as good the 100th time as the first time. And so that's a cycle that's appealing to chemical companies because there's no waste, but the quality of the product is not degraded, provided I can get good recovery of the ethylene and propylene.
Okay, thank you.
And before I forget, when we get the next question here, I want to say, we're very interested in getting students to apply to the University of Minnesota. So please keep us in mind when you're looking at graduate schools. Email me if you're thinking of applying. I can tell you about Minnesota. I can tell you it's not that cold of a place to live if that's what makes you worried. We've taken students from all over the world, and we'd be grateful if you guys considered us when applying.
Thank you, Professor, for the invitation. I know that we are all very grateful for that invitation. Well, I don't know if anybody else has a question.
I'll tell you, it gets very hot here in the summer. It gets like 95 degrees Fahrenheit. So.
Yes. Well, I had a question of my own. It was related to the experimental setup that Professor Victor already asked that, because I was thinking that the relative binding energy was taken from in situ experiments of XPS, but no, it is you get the values from this experimental setup that you're showing, right?
To get the binding energy?
Yes. How do you get them?
Here.
That graphics from relative binding energy and turnover frequency. It is a medium value, an average value.
So this is an experiment here, and this is an experiment here, but everything else is a simulation.
Okay.
Yep.
Just to clarify a little bit, Mary has experience with XPS, and then there you express the energy in the spectrum as binding energy.
Yeah.
So this is when you haven't kind of change or consider that binding energy is used as a variable for other kind of descriptions. I think that this is what got her maybe a little bit confused, because we're talking about binding energy for the reactants on the surface, if I understood well.
Yep.
And her question is, how do you calculate those binding energies?
Yeah. I have a whole work that to keep this small enough that it's not overwhelming. We have a whole nother work where we do DFT calculations of molecules on surfaces. And we can do things like apply electric fields or change the electron density of the surface and understand how those change in binding energy. Now, many other people before us, like Professor Manos Mavrakakis at the University of Wisconsin, has studied this for the past 2 decades. And he looks at how surface strain changes the binding energy of a surface. We can also look at cavities. So I could take a structure like this. This is a moth. And I can put a molecule into it and change its structure and calculate its interaction with the walls. So there's just hundreds of ways to do it, but it's all done with DFT. One more point, though, is that for this is the adsorption enthalpy. This is measured experimentally using temperature-programmed desorption. It could also be measured using calorimetry, and there are other techniques as well. So there are ways to get it experimentally. There are ways to get it computationally, and ultimately, I want to put this all together for a full picture. If people want to read about this, if they read one paper, this is the one right here, okay? And it's available in ACS Catalysis, but it's not open access, so I usually show people this. And when they look for this, they'll see the full paper.
Thank you for the answer.
Sure.
And if there is no more questions.
Okay, I think that there are no more questions for the moment. Okay. So I will only ask the participants to please turn on their cameras and to say hello to Paul and to give him an applause for his presentation, to thank him for for sharing
Vengan
with
a
us today all this
Vengan.
nice work.
Sure. Thank you, everybody. It was a pleasure.
Yeah. Thank you.
And wish us luck in our election. So, all right. Thank you, everybody.